Yo, welcome back. All right, here we go. We are going to do some practice problems dealing with average rate of change and instantaneous rate of change. So let's start with question one. It says if f of x is a continuous function having selected values of x from the table below, find the average, let's get that pen rock, and find the average rate of change on the closed interval 2 to 4. All right, and then it says, and use the data in the table to approximate. So we'll do that part second. So first, let's find the average rate of change over the interval 2 to 4. All right, so average rate of change over the interval 2 to 4, right? That's a formula. That's change in y over change in x. Specifically, that's f of b minus f of a over b minus a. So in this case, it's f of 4 minus f of 2 over 4 minus 2, right? Because this is like your A and this is like your B. So how do I do f of 4? Well, you have a table, right? If I look in this table, f of 4 is negative 84 minus f of 2, that's minus 24. You got to be careful with that. And then 4 minus 2 is obviously going to be 2, all right? So we end up getting negative 84 plus 24, right? That's going to give you negative 60. So now we're going to get negative 60 over 2, which simplifies to negative 30. All right, so there are no units in this particular problem. It's just straight up values. But if there were, and units are super important, it would be, if you think about it, how we compute this average rate of change, it would be negative 60 y units per 2 x units, or here it would be negative 30 y units per 1 x unit. Okay, so like if this happened to be miles and that was hours, it'd be miles per hour. All right, so to get the unit for that rate of change, it's always going to be the y unit divided by the x unit. All right, so now the next part of this question is pretty neat. And let's go to a different color, right? It says find the instantaneous rate of change of f of x at x equals 1. In fact, it doesn't say find it. It says approximate it. So this has to do with that picture I showed you before. You're not going to be able to get the exact value of the slope of that tangent line, so you have to approximate it. So where is 1? So 1 is between 0 and 2. Right? So if we find the slope of this secant line right here over the interval 0 to 2, this will approximate the slope of the tangent line at 1. Right? For example, not that you have to do this, but I'm going to kind of sketch, somewhat of a situation. At 0, we're at 2, and at 2, we're at negative 24. And who knows what the curve looks like? Maybe it looks something like that. So now what is it that we're doing? Well, we want to approximate the slope of the tangent line at x equals 1. So this is what we're trying to approximate, right? That's the instantaneous rate of change, the slope of the tangent line. In order to do that, though, we're going to use the slope of the secant line over the interval 0 to 2. So if I draw in the secant line from 0 to 2, right, the slope of that we are going to use to approximate the slope of the tangent line. And obviously, if I can make the interval smaller and smaller and smaller, my approximation would be better, but I'm kind of at the mercy here of what they gave me. So this is really all I can use. These are the two best points to pick here, since 1 is contained in that interval. So for this guy, when I go to show my work here, I'd say, okay, the instantaneous rate of change. Notice the difference. Here I said over an interval. Now I'm going to say at x equals 1, and this is also huge too, so huge that I'm going to make it in red, is approximately equal to, right? Because I can't find it exactly. It's approximately equal to the slope of this secant line here. So it's approximately equal to change in y values. In fact, I'll even write it this way, f of 2 minus f of 0 over 2 minus 0. So that's going to be f of 2, so that's negative 24, minus f of 0, right? That's going to be 2 all over 2 minus 0. So it ends up being negative 26 over 2, which is negative 13. So the approximation for my instantaneous rate of change is going to be about down 13 y units over 1 x unit. Okay, so that's the approximation. Again, remember, you hear me keep talking about slopes. Average rate of change is the slope of a secant line and instantaneous rate of change is the slope of the tangent line. And what we did here is we approximated that using the slope of a secant line. All right, good stuff. All right, so let's go to the next question now. So let's scroll up here. It says for f of x equals cosine x, find the average rate of change on this interval, and then again, approximate the instantaneous rate of change. So let's start with the average rate of change problem. As soon as I see average rate of change over a closed interval, right, it's slope formula. So average rate of change over the interval 0 to pi over 2, that's my AB, right? It's just going to be slope of the secant line, change in y over change in x, specifically f of pi over 2, that's like my f of b, minus f of 0, that's my f of a, f of b minus f of a over b minus a, okay? And so now I do this, f of pi over 2, put pi over 2 in the function x, we see an x, right? So that's going to be cosine of pi over 2 minus cosine of 0 over pi over 2 minus 0, that's just pi over 2. So now how do I do the cosine of pi over 2? Remember here, the whole unit circle, the north pole, that's where pi over 2 is. Here's the point 0, 1. Cosine is the x value. So the cosine of pi over 2 is going to be 0. The cosine of 0, that would be right here. That's 0 rotation, right? That point is 1, 0. Cosine, again, is the x value. That would be 1 all over pi over 2. So now dividing by a fraction is like multiplying by a reciprocal. So I get -1 times 2 over pi or -2 over pi. So my average rate of change of the cosine function over this interval is basically down 2 over pi units, okay? And we can actually see that. So before I move on to the instantaneous rate of change problem, let's go ahead and pull up the graph of this thing. So here's the graph of cosine x, and now that red secant line there represents represents my secant line, right? Over this particular interval, 0 to pi over 2, right? So pi over 2 is a little bit more than 1.5. That's exactly where we are right there. Okay, so again, what does the slope of that represent? Well, if I'm looking at the blue curve, on average, this blue curve is going down 2 over pi units, okay? All right, not too bad. So now let's get to the next part, which is a real good question, which is approximate the instantaneous rate of change. So we'll do that maybe blue. So approximate, but then again, the instantaneous rate of change. So this is different in that I don't have a table to approximate. So how would I find the instantaneous rate of change? Well, if you remember, if I do f of x, right, minus f of, in this case, pi over 4 over x minus pi over 4, this ends up getting me the average rate of change over the interval pi over 4 to some point x. Well, if I want to get the instantaneous rate of change, right, at that point, in this case, pi over 4, a, so to speak, then all I have to do is do the limit as x goes to pi over 4, all right? And that is a formula for the instantaneous rate of change. That's one way to do it. Now, if that seems a little bananas, maybe I can kind of over here do a quick little sketch where here's like pi over 4, here's x, right? Again, this isn't what the curve looks like. This is just a general picture. So maybe I have this going on. So what I do is I start with that. That's the slope of the secant line, right? So remember that's an f of x y value there. This is an f of pi over 4 y value. So f of x minus pi over 4, that's change in y's, over x minus pi over 4, change in x's. This represents the slope of the secant line. So this difference quotient here is the average rate of change. But if I take the limit as x goes to pi over 4, as this point moves closer to that point, then I occupy that limiting position of the tangent line, okay? And so that's what we would get there. I'm just going to erase that. Right? Watch the other video and you get a nice bigger picture and you get the idea. Okay, all right, so anyway, so this is my instantaneous rate of change. So let's go back to this guy. So this would be my IROC, instantaneous rate of change, at x equals pi over 4. So how would I do this now? Well, what is f of x? It's cosine x, right? So I'm going to start chucking stuff in here. So cosine x minus cosine of pi over 4, but hopefully you know that the cosine of pi over 4 is radical 2 over 2, and then all over x minus pi over 4. So now I just have to do this limit, and I'm going to get the instantaneous rate of change. The issue is this isn't the easiest limit in the world to do. If I directly substitute pi over 4 in for x, which is what I should do, I get the cosine of pi over 4, which is radical 2 over 2, minus radical 2 over 2, that's 0. And then bottom pi over 4 minus pi over 4, that's 0 over 0. So I get an indeterminate form. So you have to try something. And all the things that we've tried in the past here to do this analytically really aren't going to work here, right? So notice it said approximate. So how can I approximate a limit where everything else fails and I don't feel like using the squeeze theorem? How can I approximate a limit? Well, you can do it numerically. So you literally could make a table. So now if I come over, and again, I'm cheating a little bit here because I'm letting Desmos do the work for me. If I come over here and I look at this graph, oh, not this graph. Did I graph the, no, I didn't. Oh, you son of a gun. All right, so this was the graph of cosine x. Oh, yeah, okay. All right, I'm losing my mind. I'm losing my mind, people. Anyway, so you're like, oh, why you have two different graphs? This is the graph of the function cosine x, right? But now when I'm using Desmos to approximate that limit, I have to put in that as the function, right? Because this is what I want to approximate right here as x goes to pi over 4. So now notice there's a hole there, and that would make sense because you get 0 over 0 when you plug pi over 4 here. Now I put that hole there. Decimals won't do that for you, but I knew there'd be a hole there. That's why I put it there. Now look at what I did here. I made a table. And in the middle of that table, I said, all right, pi over 4. Well, the function's undefined there. So now let me pick values that are getting closer to pi over 4 from the left and values that are getting closer to pi over 4 from the right and see what the heck's going on here. Now look how I kind of cheated here, right? I just, instead of actually plugging this in as a decimal and hand picking decimals, I said, all right, it's just going to be pi over 4 minus some little value. Because at the end of the day, this is a number, and it's close to pi over 4. This is also a number, not as close to pi over 4. This is also a number, not as close to pi over 4. So this progression here is me getting closer to pi over 4 from the left. This progression is the opposite. It's me getting closer to pi over 4 from the right. And it looks like I'm certainly converging on something. Right? Take a look at these decimals here. It looks like maybe 0.707-ish, right? In fact, that's what we're going to go with. All right, so our limit here, and I got to lose this equal to because I wasn't able to do this perfectly analytically. Our limit's going to be approximately 707. You always want to be accurate to 3 decimal places. All right, so I had a little issue there with seeing the two graphs that I had. Hopefully that didn't confuse you. Just play the video back 1,000 times until it makes sense. All right, let's take a look at this next one. All right, so, oh my God, like the AP Calc people, they love to write these huge paragraphs, and you're like, oh, well, this is going to be a really hard problem. And really, it's going to be the same exact thing we've been doing. So let's read it. Rainfall intensity is defined as the rate at which the height of the water layer covers the ground, measured in millimeters per minute. It says the rainfall intensity at a particular weather station is modeled by the function r, and they're telling you that, hey, r of t is this function 3 cosine of t over 2, and we're using that model on this closed interval between 0 and 60, all right, where t is measured in minutes and r of t is measured in millimeters per minute. All that nonsense. All right, let's get to the question. The question is, what is the average rate of change of the rainfall intensity, which we have a function for this, it's r, over the time interval 5 to 40. So this is the interval they want the average. They define the function on that interval, but they want the average over this interval. So you're like, all right, average rate of change over the interval 5 to 40, there's a formula for that. It's the slope of the secant line, right? It's f of b. Now, I wrote f because I'm silly, but in this case, f is not f. F is r. So instead of writing f of b, I'd write like r of b. So it's r of 40 minus f of a, but again, that's r of a. So r of 5, and then all over b minus a. 40 minus 5. So this is us having a clue and using the proper function here. Not calling it F, they're calling it R. So I do this. This right here is going to be the slope of the secant line, and it's going to represent the average rate of change. And then this is just crunching numbers. All right, so I'm actually going to use my calculator for a little help here, and you can do the same. So you're going to do 3 times the cosine of 40 over 2, right? So 40 over 2 is 20. So you're going to get 3 cosine of 20. All right, and I'm just going to crunch the whole thing, to be honest. Then it's going to be minus 3 cosine of 5 over 2, right? So that'll be a number. And then when you get that number, you're going to divide that by 35. So you should do that. And at the end of the day, when you do that, you're going to get 0.1036. Now, what are the units here? So this is the first problem, where units made a big deal. We said indicate units of measure. This is actually always going to usually be a big deal. Always usually. That makes no sense, but you get the idea. So what are the units? Well, it's always going to be the y unit per the x unit. So the y unit is what? It says R of t is measured in millimeters per minute. So this would be millimeters per minute. And the x unit, or the t unit here, is measured in minutes. So it's a little weird, but your average rate of change would be millimeters per minute, which we never really would write it that way. We'd write it as millimeters per minute squared. Okay? And that's what the unit would be here. This looks a little bit confusing, so I'll rewrite this as 0.1036 millimeters per minute squared. And that is our average rate of change of this rainfall intensity function over the interval. Right? If you don't get the context too much right now, that's totally okay. We're going to get a lot more into that stuff later on in the year. All right, let's do this next question, right? A little bit of a curveball here. Let's do this one in a happy little green. So it says find the instantaneous rate of change of this function at x equals 2. Okay, so you're like, all right, how am I going to do that? Well, instantaneous rate of change, you have a formula for that, right? So you start with average rate of change. So it's f of x minus f of where you're finding the instantaneous rate of change at, over x minus 2. So that's like the average rate of change over the interval 2 to x. Now, if I take the limit as x goes to 2, right, this now represents instantaneous rate of change at x equals 2. So you're like, all right, well, how would I do this? Well, this would be the limit as x goes to 2 of f of x, which is radical x plus 2, minus f of 2, which would be radical 2 plus 2, or square root of 4, or it's just simply 2, all over, in this case, x minus 2, right? So now, what do I do here? How do I solve this? You actually have a couple of things that you can do. The one that I particularly like here would be conjugate, right? So first off, you're like, why are you even thinking conjugate? Well, because without telling you, I directly substituted, right? If I put 2 in for x, square root of 4 is 2, 2 minus 2 is 0, 2 minus 2 is 0, I get 0 over 0. So it's an indeterminate form. So what was the thing to try when you had radicals in an indeterminate form? You multiply by the conjugate. So you do radical x plus 2 over itself. So you're really multiplying by the conjugate over itself, which means you're really multiplying by 1. All right? So now when I do that, I'm going to get limit as x goes to 2. Radical x plus 2 times radical x plus 2, that's just x plus 2. These are conjugates, right? So the outer product and the inner product is going to sum to 0. I just get minus 4 there, right? And then on the bottom, it would behoove me to write this as x minus 2 times radical x plus 2 plus 2. So in other words, don't distribute in the bottom. I distributed up top because there are conjugates and good things happened, right? Outer and inner product sum to 0. The bottom I did not. Now you might be saying, well, why didn't you? Well, watch what happens, right? So plus 2 and minus 4, that's minus 2. So you get x minus 2 up top, and you're like, oh, now I get it. Now I get why you didn't distribute on the bottom, because it's clear, at least I hope it's clear, that you can now cross out this like factor right here, right? So this factor of x minus 2 goes with that factor That's great news because now I have the limit as x goes to 2 of 1 over radical x plus 2 plus 2. So now I can actually chuck 2 in. So if I chuck 2 in, 2 plus 2 is 4, square root of 4 is 2, 2 plus 2 is 4, right? So I end up getting, at the end of the day, just 1/4 here. What does that represent? That is the slope of the tangent line on the graph of f at x equals 2. How else do I interpret that? It's the instantaneous rate of change of f of x at x equals 2. Right? Not that this is necessary or did it ask us to do it, but for kicks and giggles, let's take a look here. So if I was to graph this guy, so let me pull up Desmos real quick. All right. If I was to graph this, so f of x equals radical x plus 2, right? Does it seem reasonable that at the point x equals 2, which would be 2 comma 2, right? That point right there. Does it seem reasonable that if I drew in that tangent line, that it would be up 1 over 4, that the slope of it would be up 1 over 4? And hopefully saying, yeah, it certainly seems reasonable. In fact, it is. Okay. All right. So those are some instantaneous and average rate of change problems. We have 2 homework questions for you here that I want you to do and submit. They're very similar. Question 6 is a lot like question 4. The only difference is instead of a radical function, you're dealing with a polynomial. And so the process to do the limit will not be conjugate. It will be do something else that we learned in the first unit. All right, be good. Sorry that this video was so banged up. I'll make the next one better.